we're going to have one more video to kind of wrap up the idea of two-proportion inference. So last time I encouraged you to try the next example on your own, and let's check out how you did. So in this example, we have our two different groups. We had information from 2015 and 2016. So I'm going to call those groups 1 and group 2. If you guys labeled them the other way, totally fine as well. And then they give us some information. 48% of households had some kind of subscription video on demand, like Netflix, Hulu, whatever. So that's our P1 hat, 48% in 2015, and our P2 hat, we see that rose a little to 50% in 2016. And both of these, they tell us, came from polls consisting of 1,400 randomly selected participants. So there's our N1 and N2. And something else that you might want to find off to the side is how many successes we had in each group. So if let's do group 2 first, it'll be a bit easier. So if there were 1,400 in our sample and 50% had a subscription video on demand service, then our X2, our number of successes, would just be half of our sample, or 700. Same thing for group 1. Just figure out what 48% of your sample size is to get the number of successes for group 1. All right, so it says test this claim using the appropriate hypothesis test. And specifically, we're testing the claim that the proportion, there was an increase. Sorry for the bad drawing there. All right, so testing that there was an increase. So I've got this filled out because you've hopefully tried it on your own a little bit. Our null hypothesis, write it either way. You don't need to write both. The proportions of SVOD is the same in the 2 years. Our research question is, has it increased? In 2016, did this become more popular? So P2 is going to be greater than P1. If we define P1 as 2015 and group 2 is 2016. Then our test statistic is that z-score, fancy z-score. We have the difference in the 2 years based on our data. I just want to emphasize here, however you define group 1 and group 2 to start off with, you must keep it consistent throughout the entire problem. So HA, the symbol was less than because we think fewer in 2015, more in 2016. Test statistic, make sure you put 2015 numbers before 2016 numbers. Keep the order consistent. So the difference in the two groups based on the data, minus the initial assumption of no difference. Our standard error, we need this common pooled proportion. So successes in both groups over sample size, we get average there in the middle. And 1 over the sample sizes, we get a test statistic of about -1. So we know, again, about z-scores, we know that's not really rare. That's not a huge z-score. So let's interpret that or bring that in terms of a probability. So our p-value is, what's the probability of seeing this data, this statistic, or more extreme? And remember here, HA is less than, so I'm shading less than my test statistic. And in our calculator, that's normal CDF from -infinity to our test statistic, and that should give us 0.1450. So if the null's true, if there's no difference in the proportions for the 2 years, if the null's true, we're going to see data like ours, that's our test statistic, or more extreme, that's the part we shaded, 14.5% of the time. So if the null's true, we have kind of a decent chance of seeing our data. So if the null's true, we have a decent chance of seeing our data. So that means we have little to no evidence. Go back and flip in your notes if you need that reference again on the bottom of page 68. We have a big p-value, so it's not rare enough to have evidence for HA. And remember, HA is proportion of subscription video on demand services is bigger in 2016. We don't have evidence for that. All right, the problem did not ask you to do a confidence interval, but I did go ahead and work one out just for an extra example. So thinking about this, we said we had little to no evidence that it's actually increased or bigger in 2016. So if we come up with an interval that should contain the value of 0. We can't say that one is in fact bigger than the other. There may be no difference. So when we calculate the interval, we expect 0 to be in there because we cannot prove there is a difference. So again, just for example, I worked out a 90% confidence interval. Our point estimate is the difference in group 1 and group 2. So between 48 and 50%, there's our point estimate here. For 90% confidence, here's our multiplier. If you need a reminder, that was inverse norm. 90 in the middle, so 10 on either side, split that equally, you get 5%, and take the positive version of that. And then our standard error, cannot emphasize enough. Hypothesis test, we have a standard error that assumes the two groups are the same, and we had to do that extra work off to the side to calculate that common proportion. Confidence interval makes no such assumption, so just leave it as your two separate groups and then follow that through. And you'll notice 0 is in our interval. One side's negative, one side is positive. So 0 is in between a negative and a positive number. So interpreting that, we are 90% confident the difference in proportions is between, and go ahead and write the negative down, negative 0.051 and positive 0.011. And again, that sounds kind of weird, and that's fine. That means we cannot conclude there's a difference because we have 0 in our confidence interval. So I hope one more example was helpful, and hopefully you guys did pretty good on your own. Let's check out the next page to kind of wrap up some closing thoughts here. So starting with these bullet points towards the middle of the page, they give us some scenarios. They tell us if the null is true in real life, what kind of test statistic should we get? And by that we mean, are we going to get a big test statistic, a small test statistic, what kind of value? So think about our test statistic, how that's generally written. So it's generally written as our data or our point estimate minus our initial assumption, the null hypothesis, over the standard error. So if the null is true in real life, when we go out and collect data, what's our data going to look like? If the null is really the reality of the situation, our data should be close to that. So I'll say data close to the null. If the null is actually true, the data should match that pretty well. So when we come up with our test statistic, we're looking at the difference between two numbers that are really similar. If the data is close to the null, then this difference is going to be pretty small. We're going to have a small difference between those, not a big discrepancy, so our test statistic should be small. On the other hand, if the null is false in reality, so this time our null is false, it does not represent the underlying reality of the situation, then when we go collect our data and find our point estimate, then our data should be far from the null. Far from the null. And when we look at that discrepancy, when we subtract the two, we're going to get a really big difference. Data is not matching up with the null because the null doesn't represent reality. So we're going to get a large test statistic or a big discrepancy. Okay, one more before we pop up to the top here. This is asking about the magnitude of our test statistic, so forget if it's positive or negative, just how far from 0 it is. We want to know what happens to our p-value. So let's kind of explain this via picture. So maybe I've got a test statistic here of, -2. So, and this should say on a two-sided test specifically. So if my test statistic is -2, then my p-value is going to be these extremes. Then, if we are interested in the magnitude of the test statistic increasing, the greater the magnitude, that just means we're getting further from 0. So maybe now I'm at -3 for my test statistic. And we'll consider both sides because we're talking about a two-sided test. My p-value is going to be these extremes now on either side of plus or minus 3. So what happens to our p-value? As our test statistic gets pushed further from 0, the area we're talking about gets less and less. So the greater the magnitude of the test statistic, the smaller the p-value. All right, to answer the last question, we need to pop up to the top of the page and define a couple of terms here. So I'm going to draw sort of a grid here, attempt to draw a grid, and I'm going to represent 4 different scenarios in this. So across the top, we're going to represent our conclusion or decision of the test, our hypothesis test. And I'm going to put this in terms of the null. On this side, we're going to talk about what's happening in reality. So we know, since we only have a data set, a sample, we might make a mistake in our conclusions and our predictions. So we're going to talk about what those mistakes are called here. So in reality, we've got a couple of options. One is our initial claim might be true. HO is true. The other option is that our initial claim is false, HO false. When we conduct our hypothesis test, we might come up with something like this. HO is unlikely. And remember, that happens when we have a small p-value. Or I might have something like the null hypothesis is likely, which is when I have a large p-value. And for purposes of this class, we'll just say small and large is less than 10% or bigger than 10%. So follow me through here. If the null is true in real life, we collect our data and come up with this idea that we get a small p-value and say, if the null is true, it's very unlikely to see our data, so the null's probably not true. We've clearly made a mistake. In reality, it's true. We're thinking it's highly unlikely. That's a mistake, and that type of mistake is called a type 1 error. On the other hand, if the null is true in real life, we collect some data and get a big p-value. We can't rule out the null. It's possible. So no mistake. Those kind of match up with each other. Null's true. We can't rule it out. Sure, those match up. If the null is false in real life, we collect some data and say the null is highly unlikely. Those also match up. No mistake. However, if the null is false in real life and we collect some data and say, there's a decent chance of seeing that data under the null, we can't totally rule it out, then this is an error, and specifically this is a type 2 error. All right, so know those definitions, and let's check out one example related to this. So at the bottom, revisiting one proportion hypothesis test, this concept applies across all hypothesis tests. It says we've obtained a p-value of 0.201, and remember what that means in terms of our conclusion. 0.201 is a larger p-value, meaning we can't rule out the null. Cannot rule out HO. If the null's true, there's a decent chance of seeing our data, so we can't rule it out. It's possible. On the other hand, so we've got our decision. Let's check out reality. They tell us if the population proportion is actually 0.24, so reality, p equals 0.24, check out our null. Up here, our null says it's 0.2, so in reality, the null is false. It's really 24%. Our null says it's 20%, so in reality the null is false. We decide that we cannot rule out the null, so check out our definitions up here. Null is false in reality. We decide we can't rule it out. It's a possibility. So we have committed an error. Those guys don't match, and specifically a type 2 error. So our mistake in this, type 2 error. All right, this wraps up our inference for 1 and 2 proportions. In the next set of videos, we're going to repeat all of this stuff in the context of 1 mean and 2 means.